Here I show the example. So, the same sequence I give AAT, CTA, TA, this is second one AA, GA, TA, right. If I want to align these two sequences without introducing any gaps, how many ways we can align? 3 ways, because I do not want to introduce any gaps. So, first sequence I put here, second sequence here I put the left side, right, at the leftmost side, and here I put it in the middle, and here I put the right side. Now, we see which method is the good, which alignment is the best. So, we use some scores. For example, if you take match score 1 or if the sequence 1 and sequence 2 are same, if the residues are the same, then we give match score 1. We put the match score 0 if they do not have any match, if there is any change. If the residues are the same, we give score 1, if the residues are different, we give score 0. So, in this case, if you take the first alignment, how many matches? 1, 2, 3, 4 matches. So, the score will be 4, because all the mismatch we put 0. So, 4 plus the 0, that is equal to 4. If you take the second example, what is the score? 1, because only one match. And with the third alignment 3, right, 1, 2, 3, match will be 3, right. So, we have the identity matrix, we use ATCG. So, if it is same we put 1, and if it is different we put 0, right, that is fine. Now, if you introduce gap, why do you want to introduce gaps?
To better align.
Better alignment, right. So, if there is some changes, right. So, we need the gaps. So, in this case if you do the gaps, how many different ways you can align these two sequences? We are here the length is 1, 2, 3, 4, 5, 6, 7, 8, right. So, here we have length as 3, 6. So, how many different ways you can align these two sequences if you introduce gaps? So, there are various ways. So, there are 28 different ways you can align these two different sequences. So, I show an example. Okay, this is sequence 1, here sequence 2, this sequence 3. Here I put 2 gaps here, one gap is here, one gap is here. Here also the same here, right. Here you put the gap here, here you put the gap here, here these 2 gaps are similar together. So, here we have to give a penalty. The previous alignment we give the match score and we give a mismatch score. In this case here we have the gap. So, we need to introduce gap penalty. So, here I put -1 if there is a dash either in the first sequence or in the second sequence. Then match score 1 the same as before. So, if this is equal to sequence 1 equal to sequence 2. So, if there is a mismatch you can put the mismatch score. So, you can put the mismatch score if sequence 1 is not equal to sequence 2. If you do this, what is the score for the first alignment? So, this is 1, 2, 3, right. For the alignment match score is 3, this is -1, this is -2 and others are 0, right. So, this will be 1. So, we take this alignment. So, what is the matching score? 1, 2, 3, 4, 5, -2,
3,
okay, plus 0, this is equal to 3. So, about this one? 1, 2, 3, 4, 5, 5 minus 2 plus 0, this is equal to 3, right. So, if the earlier alignment we got the score here without gap. So, we get the score of 4, 1, 3. Now, we aligned with the gaps. So, we change the score, we get 1, 3, 3. Now, next question is, okay, if you have these gaps and if you have this mismatch, whether we need to give same weight or different weight. Before that, I give another example. So, here we have the protein sequence. So, here I give the DNA sequence and I give another protein sequence here. This is sequence A, here sequence B. There are different ways we can align the two sequences. So, I found the first one. So, I put some gaps in the sequence A and the sequence B. In the second alignment there is no gap in the sequence A, but some gap in the sequence B, and the third one we introduce gaps. So, we take the one example. So, if you take the first alignment, so this is same, T and T are same, I and I are same, this T and T are same. So, here this will be 1, 2, 3, 4, right, and here this is a gap, So, minus 1, this is a gap minus 1 and here again a gap, this minus 1. So, 4 minus 3 that is equal to plus 0, that is equal to 1. The second one, so we did not give gaps. So, in this case here this is 1, 2, 3 minus 1, this is equal to 2, right. So, if you compare the alignment between 1 and 2, what is the difference? Gaps, right. So, difference is gaps, because of the gaps we give the penalty. So, this is why alignment 2 is better than alignment 1. So, we try to minimize the gaps and maximize the score, right. This we can do in several different ways. So, now another issue is we introduce gaps, right. If you see this alignment, so we introduce gaps, but there is a difference between the introducing the gaps. If you see the first alignment, how many gaps we introduced? 2. 2 are the same position or different positions? How many different 2 different times we introduce gaps? This one time we introduce here, second time we introduce here. Here we introduce one time here and second time here, and third one we introduce gap together. So, if you look into these evolutionary rates or look into this the origin of different organisms, right. So, getting continuous gap is more closer than introducing gaps at the different regions, or otherwise if you have insertions or deletions which happen at different places are less probable than having these insertion deletions at together same stretch together. So, if we want to take into this account, what we have to do? Yeah, we have to give some penalties for the origination gap and we have to give penalty for each gaps, right. So, we will do that. So, if we have 2 sequences in arbitrary sequences, one is 12 residues and 9 residues. So, we have shortage of 3 residues. So, we have to introduce 3 gaps, either these 3 gaps can be together or we can separate the gaps here and there. So, if we have the homologous sequences and some residues are missing at the N terminal or the C terminal, in this case we can keep these 3 residues, right, either insertion in one sequence or the deletion in other sequence, right, at one place. So, in this case we can cover other sequences. In this case we give penalty based on the gaps where we introduce. So, I give an example, right. So, one is origination penalty. So, that depends upon the gaps we introduce. Here for each series of gaps where we introduce in a sequence, we give a penalty that is called origination penalty. And the second one is length penalty, that is number of missing characters. When the sequence 1 and the sequence 2, when you align each other, how many places where it is not aligned, how many places you have the gaps. Okay, so, now we gave the 3 sequences, the same 3 sequences. Here we have the gaps at 2 different places, and here also we have the gaps at 2 different places, and here the gaps are at the same place. So, if we take the origination penalty of minus 2, because we are introducing, right, we do not want to introduce because nature does not want to select these insertion deletions. So, we give the penalty of minus 2, a length penalty of minus 1 and the match score of 1 and the mismatch score is 0. If you do this, what is the score for the first alignment? What is the match score? 3. Mismatch score is 0 anyway, and what is how many origination penalty?
2 into minus 2.
2 times, right, one we originate here, one we originate 2 here, right. So, plus 2 into minus 2, right, and plus how many length penalty? 2 times multiplied by minus 1. So, this will get 3 minus 4 minus 2, right, minus 2. So, minus 6, 3 minus 6, that is equal to minus 3, all right, fine. So, now we take the second one. So, here what is the score? 5
plus 0
minus 4 minus 2, right, fine, this is equal to minus 1. If we take the last one, so here 5 minus 2 minus 2, correct, this is equal to 1. So, if you compare these 2 alignments, here we introduce only once, here introduce twice, right, as per the selection by the nature, right, we can, this will prefer this alignment than this one because we insert 2 times here. So, here we have the better score than the other ones. Here we use the very simple one, putting the value of 1 and minus 1 for the penalty, right, and minus 2 for the origination penalty and 0 for the mismatch. But is it reliable, right? So, if you give just 1 and 0, is it fine for the alignment, right, because 1 and 0. So, but that we can change. For example, if you in the case of nucleic acids, right, so for the DNA. So, how many different bases? 4 different bases. So, the current scenario, whatever the changes, we give the same score, but that is not reliable, right. Sometimes we change purine by purine, sometimes we change pyrimidine by pyrimidine, sometimes we change purine to pyrimidine and pyrimidine to purine. Likewise, in the amino acids, different types of changes. For example, if you replace alanine by valine, so there is an effect, because alanine is a hydrophobic amino acid, valine is hydrophobic. What is the difference between these two? Side chain. This is bulkier than alanine. Alanine is only one CH2 group, valine is 3, so we have the bulkier group. But if you replace alanine by lysine, this is positive charge. So, here this is hydrophobic, this will change the environment. So, it may not be good to have the same score if you replace alanine with valine or a lysine, right. So, we need to consider the effect of the mutations. So, in this case we have to give the scoring in a different way, right. How to do that? But in the blast, sometimes they use the same nucleotides have score 5 and the difference have 4, or we can give the mild reward plus 1, or we can give the score of minus 1 in the case of transitions. What are transitions? What is called transition? Purine to purine, like ARG, right, or pyrimidine to pyrimidine, okay, C or C, right, they change vice versa. Then there is another called transversions. So, that means purine by pyrimidine and the pyrimidine to purine. Why they give the penalty of minus 5 and minus 1? Right, because what is the definition for the purines? Right, but the pyrimidines they have how many rings?
Purine 2 rings, pyrimidine 1.
Purine 2 rings, pyrimidine 1 ring. So, if here you are changing 2 rings to 2 rings or 1 ring to 1 ring, that is fine. This way they put the penalty of minus 1. And the other way, if you change the other way around, so 1 ring with the 2 rings or 2 rings with 1 rings, so it may create either the crowded situation or that is totally free. This way they do not avoid the situation, so they put minus 5. Okay, now these are matrices. So, here these are the 4 nucleotides, right, ATCG. So, earlier we used 1 1 1 1. Now, we change it, right, this is if it is score match score we put 1, right. If it is purine to purine or pyrimidine to pyrimidine we give minus 1, right. If it is other way around purine to pyrimidine or pyrimidine to purine, so we give minus 5. If you make this score, what will happen in the alignment?
Mostly those alignment will be preferred where purine to purine.
Right. So, either they try to match, or if you want to mutate, they try to make the similar type of amino acid residue or nucleotides. They avoid the other way around, because some instances we have to cannot avoid, in this case we use, but in this case we give less score, this is minus 5. Okay, this is for the nucleotides. What will happen in the case of amino acids? How to deal with amino acids?
There will be 20 cross 20 matrix.
Right. So, we have 20 different amino acid residues. So, 20 different amino acids are classified in 2 major groups. What are 2 different major groups? Hydrophobic and hydrophilic, and hydrophobic we have different groups like aliphatic or aromatic or sulfur containing residues, right. In the aliphatic this hydrophilic, positive charge, negative charge as well as the polar, right. So, now we can see the mutations whether these 2 amino acids, right, or both have the aromatic functional group. So, in this case we can give a good positive score, or we can give non-polar functional group with a charged group. This is the aromatic to aromatic, right, that is fine, aliphatic to aromatic is fine. So, with there is non-polar group with the charged group, here we get penalty because they alter the situations, right, this alter the stability or alter the function, like we discussed in the case of sickle cell anemia. So, what is the mutation?
Valine 6 to
glutamic acid 6 to valine, right. So, it causes diseases, right, sickle cell anemia. So, in this case we need to give penalty, so that we can align like this. Okay, then what are different ways to have these matrices. So, you have 20 different amino acids, right. What are the possibilities of changing a specific amino acid to other amino acids, right. Either you can change the hydrophobicity like just we discussed, or you can see the charge, or you can see the size. Small amino acid to small amino acid, here they do not care about the hydrophobicity, but they give the small residues like serine to alanine or glycine to serine, or they are the bulkier groups lysine to phenylalanine, right. So, they give the size, right, they can derive the matrices, right, they can allow. Then another option is the genetic code. So, how many nucleotide substitutions are necessary to convert a codon to an amino acid, right. So, how many nucleotides?
3.
Right, totally 4 nucleotides, right, ATCG, right. So, 4, but how many amino acids? 20, right. So, in this case we discussed earlier about the genetic code. Some cases we have only one mutation, sometimes there are 2, right. So, depending upon number of substitutions in the nucleotide that lead to the amino acid. So, we can accordingly you can change, okay, single substitution they group together, 2 substitutions they group together, right. Likewise, they can make the genetic code to see how you can reliably you can align the protein sequences. And the common method, right, so you can align with the hydrophobicity, you can align with the size, you can align with the charge, you can align with the number of changes in the codon. But the common method to derive the scoring matrices is mainly they check the substitution rates, actual substitution rates. For example, I showed the my hemoglobin sequences, take the actual sequence and just align and then see what is actual rate, how many times alanine is mutated to valine, how many times alanine is mutated to aspartic acid. So, they take the real ones and from these real cases they derive the matrices. How many, what is the probability of a specific residue A to be mutated to the residue B, right. So, if it is high or low in the real cases, right, for take the different organisms. So, based on that they derive the matrix, okay. This is called the scoring matrices. Okay, how to do that? So, in the alignment, if the residues are aligned quite frequently, okay, they give the positive values, and the alignment if they are not observed, in this case we need to penalize. So, we give the less score. So, how to do this? From the alignment of different sequences of various homologies, right. Homology means how far they are similar, right, that I will discuss in the later classes. So, they derive a matrix that is called the point accepted matrix, mutation matrix, right. This matrix is called the PAM matrix. What is the PAM matrix?
They will derive like scores on the basis of how frequent the mutation occurs.
Right. So, this is PAM stands for point accepted mutation matrix, right. So, you can see you can derive the some PAM matrix, right, by the substitutions that occur in the alignments between similar sequences. So, if we have sequence 1, sequence 2, several pairs of sequences, right, some of them you can see 100% match, some the 90% match, some the 80% match, right. They use different types of sequences with the different matches, for example 90%. So, we take all the sequences which have the similarity of more than 90%. In this case, if there are 10 residues, 9 will match, 1 is different, right. If there are 100 residues, 90 will match. If you take the 100 residues, if it is 90% sequence identity, so 90 will match, right, 90 match, and 10 mismatch, and this take this 10 and see the rate, which residue in sequence 1 is mutated to which residue in 2, right. So, if you look at this very carefully, there are 2 sequences, right, sequence 1, sequence 2, for example AITV. So, here AATV, what is the substitution?
I to A.
I to A. If I take this as sequence 1 and this as sequence 2, then what is substitution? A to I. So, it is changed. So, when they derive the substitution matrix, say they do not care whether this is from one sequence or first 2 or 2 to 1. So, they treat this as similar. So, for the development of the PAM matrix, this way they get the diagonal matrix. So, we get one side will get the data, so second side is this mirror image of the other, right, there is a get the diagonal matrix. So, they usually use the sequences with more than 85% sequence identity. In this means, if you have 200 residues, how many residues have minimum minimum number of residues are aligned?
70.
If you have 200 residues, 170 residues should be have aligned, right, 200 residues. right, or more, this is minimum. So, then they get the changes and see how far the changes happened, right. So, then how to construct a matrix? First you have to see the relative mutability, that means for specific amino acid residue A, for example alanine, how far this A is mutated to other residue, what is the frequency of the residue A to be mutated to other residues or any of the other 19 residues. Then the second one we need to think about how far this alanine is mutated to in specific residue, how many possible substitutions alanine can make, 19, right. So, the 20 amino acid residues. So, if alanine is mutated, there are 19 mutations, there are 19 different possibilities. So, now the question is what is the possibility of mutating alanine to glycine or alanine to lysine, right, if you align the sequences, right. So, get the 95% sequence identity. So, we check the sequences and then see how far they are aligned. So, this is AIJ, for example, if there is the ACM, what is the meaning of ACM?
C mutated to
How many times, right, cysteine is mutated to methionine, right. So, methionine is replaced with cysteine, right, how many times they have this mutation cysteine to methionine, right. Now, this is the specific mutations in the alignment, that depends upon how many times the cysteine occurs in the sequence and also how many times the cysteine is mutated to other residues, right. So, we need to consider all these aspects to derive the PAM matrix. So, for example, if you take the any sequence, for example, if you take alanine to glycine, what are the different aspects we need to consider to derive the PAM matrix? Frequency of alanine, right, first we need the frequency of alanine and then mutation frequency of alanine. So, this one, and second one is how many times A is mutated. So, mutation frequency and then how the specific pairs, right. For example, how many what are the preferred specific mutations, for example, the mutations A to G, right. We need to consider all these aspects, right, to derive the PAM matrix. So, now we normalize the frequency of occurrence of each amino acid and finally take the log of the each values, this will give you the PAM matrix. Why do you take the log? Yeah, because otherwise you will get log numbers. So, in this case we can explain, right. So, in this case in the log scale, so you can explain the probability of each amino acid residue to be replaced with the other residues in the evolutionary rates. So, we have different matrices, for example, PAM 1. So, this means one substitution per 100 residues, right, this is called the PAM 1 matrix. This is also called log odds matrix, right, because the entries are based on the log of the substitution probability. Then let us see how we derive the PAM matrix. I will show an example, right, and we will derive the matrix, right. For example, if we have the 10 sequences, we align the different sequences, right, and then see what are the different mutations and how we account these mutations to construct the PAM matrix. So, essentially if we take PAM 1, right, this is compare the sequences which are closely related, that means they take highly homologous sequences, and if we take the PAM 1000, this mainly with the distance relationship. So, they use various levels of sequence homology to derive the matrix. Normally you can use PAM 250, this is the usual ones we use for any alignment, right, for the generally aligning two sequences. Okay, now we will see how we derive the PAM matrix. So, what is essentially PAM matrix? What is the expansion for PAM matrix? Point accepted mutation matrix, right. So, now what is how the matrix looks like? 20 by 20 matrix. So, all the 400 elements are different or anything similar? Symmetric, right, because a diagonal matrix, right, because of the reason I explained earlier. So, you can get symmetric matrix, right. So, now we have different sequences, sequence 1, 2, 3, 4, 5, 6, 7. I give the different sequences, and from different one sequence to another sequence you can see the mutation. So, from 1 to 2, so the position number 1 A is mutated to glycine, right. For example, if you take this one here A C G C T A F K I, right, this is 1, this go to 2, what is the mutation? A is mutated to G, right. So, now here the sequence is G C G, rest is the same, right, CTA FKI. Then the third sequence we get one is right. So, here the mutation is I to L right. So, here this is the change. So, we get this sequence ACG CTA FKL. Now, the second one we make another changes A to G right. So, here make changes A to G right, we get this sequence GCG GCG CTG FKI right. You can see the change C to G, this A to G right, fine, A to G, this is the A and here you change to G, and here you can see the change to A to L, this is the A here and here is the L. So, here A to L, and then we go to the other different mutations. The third one, that is C to S right, from here C to S, and the last one you can see G to A here, G to A. So, you can construct a tree depending upon the substitutions in each sequence. So, I think I will discuss the development of the PAM matrix in next class. So, first we recap. So, what are the different aspects we discussed in today's class? Yeah, first alignment. What is an alignment?
Comparison of two sequences.
Comparison of two different sequences, right. So, when you compare two sequences, say sequence A and sequence B, what are the various different changes?
Mutations.
Mutations. What is the mutation?
Substitution.
Is substitution, right, change of one nucleotide or one amino acid by the other one, right. So, what is insertion?
One or two nucleotides.
Yeah, one or more nucleotides or amino acids that are inserted inside the sequence. What deletions?
One or two amino
Yeah, amino acid residues or nucleotides are deleted from the first sequence, right. So, there are different ways. Then how to align sequences, we discussed about different aspects. First one, we have two sequences of different length, right, if we can align without any gaps, and second aspect we introduced a gap right at different places, right, and the third one we discussed the difference between the origination and the gap penalty, how many gaps and how many times we introduce gaps, right, based on that we aligned. Then for the scoring, there are various ways to score. The first one is for the if you take nucleotide. So, what are different ways to score? Transitions or the transversions, right, as well as the match score, right. In the case of amino acids, what are the different ways to score?
matrices.
Based on hydrophobicity, based on charge,
Size.
based on size, and based on the changes in the codons, and the actual one we can check the evolutionary rates. If you align two sequences, what is the actual changes from one sequence to second sequence, right. So, based on that we can derive PAM matrix. So, what are the various factors one has to consider for the development of PAM matrix?
Frequency of
Frequency of amino acid,
mutation.
frequency of mutation, and the probability of specific mutations, right, and we need to have some normalization factors to finally take the log to get the log odd matrix, right. This PAM matrix is also called log odd matrix, right. Then for the specific example we will discuss next class. Thanks for the kind attention.